Hello, welcome back to the playlist of videos on hypothesis testing. In this video, we focus on the third lecture, namely applying the concepts. How do we go about applying the concepts that we have so far learned and additional concepts that are required to arrive at the decision? Let's get into the video. In the previous two lectures, we understood in detail on the following two topics. Primarily, on choosing one among the three possible inequalities, that is not equal to or less than or greater than in the alternative hypothesis, and assessing type 1 and type 2 errors, the relationship between them, their consequences, and the strategy to choose the correct value for alpha. In this lecture, we will focus on how to use a point estimate, that is a single sample statistic, to judge if the population characteristic is sufficiently deviated from the hypothesized value in order to reject the null hypothesis, how to use the point estimate to arrive at the p-value, how to compare the p-value and alpha to make the decision between H0 and HA, and how to apply the above steps when the population characteristic is population proportion of success or the population mean. Population characteristic in the hypothesis statements above is often unknown. As already discussed, if the population characteristic was known, then we do not require hypothesis testing. Decision can be made instantly. Since it is unknown, the population characteristic is estimated using sample data. Often, the population characteristic in the hypothesis statements is either the population proportion of success pi or the population mean mu. Population characteristic is estimated using a sample statistic, that is the point estimate, from a sample data. Refer previous lectures on point estimate and confidence interval part 1 and part 2. Sample mean x bar is the sample statistic or point estimate that is used to estimate the population mean mu, and the sample proportion p is the sample statistic or the point estimate that is used to estimate the population proportion of success pi. Distribution of a sample statistic, that is sample mean x bar or sample proportion p, follows a normal distribution when the sample size is large enough, where the mean of the sample statistic distribution equals the actual population characteristic mu or pi. Note, if we know the mean value of the sample statistic distribution, we will come to know the actual population characteristic mu or pi. Since the mean of the above distribution is only estimated using the point estimate x bar or p and the confidence interval, the value actual population characteristic also is not known precisely. But we can still make our decision using probabilities. We will learn how. The null hypothesis H0, that is population characteristic equals hypothesized value, claims that the population characteristic is same as the hypothesized value. Therefore, if H0 is true, then the population characteristic mu or pi equals the hypothesized value. In other words, the sample statistic distribution is centered around the population characteristic, which also happens to be the hypothesized value when H0 is true. The sample statistic x bar or p for a sample drawn at a given time is a chance outcome of sampling and can take any one value within this distribution, depending on the sample drawn from the population at that time. The sample statistic x bar or p can be close to the mean or far away from the mean. The probability of getting a sample statistic x bar or p closer to the mean is quite high, as evident from the distribution, while the probability of getting a sample statistic x bar or p away from the mean is quite low. Since the exact value of the population characteristic is not known, but the hypothesized value is known, a sample statistic x bar or p from a given sample can result in one of the following two cases. Case A, where x bar or p is close to the hypothesized value, or Case B, where x bar or p is far from the hypothesized value. We have chosen the values of x bar or p higher than the hypothesized value for illustration. They can as well be lower than the hypothesized value. Therefore, the discussion that we carry on from now applies both to sample statistics that are higher and lower than the hypothesized value. Case A, where the sample statistic x bar or p is close to the hypothesized value. The probability is quite high that x bar or p is close to the mean of the statistic distribution, which is also the same as the population characteristic mu or pi. It is the characteristic of a normally distributed probability distribution that the frequency of arriving at a sample statistic close to the center of the distribution is quite high compared to the edges of the distribution. X bar or p is close to the hypothesized value in case A, and the high probability that x bar or p is also close to the population characteristic implies that the hypothesized value and the population characteristic are close to each other. The best case is they are the same or equal. Therefore, it is difficult to reject the null hypothesis H0, which claims that the population characteristic equals hypothesized value when x bar or p is close to the hypothesized value. In other words, the evidence from the sample is not sufficiently strong enough to reject H0. We fail to reject the null hypothesis H0, that is population characteristic equals hypothesized value in case A. Note, failing to reject H0 does not mean accepting the null hypothesis. We never accept the null hypothesis, because failing to reject means they are not far away enough from each other to reject. It is not the same as accepting population characteristic equals the hypothesized value. They are close enough to each other. Both are not the same or equal, which can only happen as a best possible case. Case B, where x bar or p is far from the hypothesized value. As discussed for case A, since the probability is quite high that x bar or p is close to the mean of the sample statistic distribution, that is the population characteristic mu or pi, the center of the sample statistic distribution gets closer to x bar or p and away from the hypothesized value. In case B, x bar or p is far from the hypothesized value, and the high probability that x bar or p is close to the population characteristic implies that the hypothesized value and the population characteristic are far enough from each other. Therefore, there seems sufficiently strong evidence from the sample to reject the null hypothesis H0, which claims that population characteristic equals hypothesized value. Therefore, we reject the null hypothesis in case B. Rejecting null hypothesis simultaneously favors the alternative hypothesis HA, which in this illustration is as follows. It is highly possible that this sample statistic x bar or p does not belong to the distribution that is centered around the hypothesized value, instead to another sample statistic distribution whose population characteristic mu or pi is greater than the hypothesized value, thus favoring the alternate hypothesis HA, which claims mu or pi is greater than the hypothesized value, while rejecting the null hypothesis H0. Another argument can be placed for a sample statistic x bar or p that is far below the hypothesized value, that it belongs to another distribution whose population characteristic mu or pi is less than the hypothesized value, favoring the alternative hypothesis HA that claims mu or pi is less than the hypothesized value, and also supporting the conclusion that H0 be rejected. We have used the generic terms like x bar or p is close to the hypothesized value or far from the hypothesized value while having to make the decision between H0 and HA. We need a reference value, often referred as the critical value for the sample statistic x bar or p, beyond which we qualify the deviation from the hypothesized value as close to or far from. In any of the three following cases where H0 is rejected in favor of HA, that is mu or pi is less than hypothesized value, or HA, that is mu or pi greater than hypothesized value, or HA, that is mu or pi not equal to hypothesized value, that is x bar or p is far from the hypothesized value on either direction, the critical value x bar star or p star should be chosen so that the decision is made between H0 and HA. In a hypothesis testing where HA is mu or pi greater than hypothesized value, the critical value x bar star or p star not only decide the sample statistic x bar or p value above which H0 is rejected, but also alpha, the probability of the type 1 error. Alpha, the probability of the type 1 error, is the shaded area under the distribution curve to the right of the critical value x bar star or p star. While choosing a critical value x bar star or p star, one invariably lands in a situation wherein H0 is rejected alpha percentage of times even when H0 is true. The reason for this is a sample statistic x bar or p greater than or equal to x bar star or p star by choice is not considered as a chance variant, even though it is, in a distribution that is centered around the hypothesized value due to its extent of deviation from the hypothesized value. Therefore, H0 is rejected even when H0 is true alpha percentage of times. Similarly, in a hypothesis testing where HA, that is mu or pi, is less than hypothesized value, the critical value x bar star or p star decide the sample statistic x bar or p value below which H0 is rejected, and also alpha, the probability of type 1 error. Alpha, the probability of the type 1 error, is the shaded area under the distribution curve to the left of the critical value x bar star or p star. Like in the previous case, H0 is rejected alpha percentage of times even when H0 is true. Similarly, in a hypothesis testing where HA is mu or pi not equal to hypothesized value, the critical values for the sample statistic decide the values on either side of the hypothesized value beyond which H0 is rejected. Alpha, the probability of type 1 error in this case, equals 2 times the shaded area under the distribution curve to the left and right of the symmetrically positioned critical values CV left and CV right. Recall, while discussing on type 1 and 2 errors, we stated that type 1 error is controllable. It is by controlling alpha that type 1 error is controlled. Alpha in turn decide the critical value x bar star or p star. In practice, we choose the value for alpha, not the critical value x bar star or p star. X bar star or p star is in turn decided by the chosen value of alpha. Alpha as a percentage value is a carefully chosen one. We discussed how to strike a balance between type 1 error, that is alpha, and the type 2 error. Having decided on alpha, the other value that we derive is the sample statistic x bar or p from a sample data. How do we use x bar or p as against alpha and make the decision between H0 and HA for each of the following 3 cases of alternative hypothesis, that is mu or pi greater than hypothesized value, or mu or pi less than hypothesized value, or mu or pi is not equal to hypothesized value. Let's start with the first case, case 1, with a hypothesis test where the alternative hypothesis HA is mu or pi greater than hypothesized value. Sample is drawn from the population and the sample statistic x bar or p is computed. Area under the statistic distribution to the right of x bar or p, that is the shaded area, is evaluated. This shaded area provides the probability of getting a sample statistic as extreme as the current one, meaning the current value and values higher than the current one from the hypothesized value. This area is compared with alpha, that is the shaded area above. If the area to the right of x bar or p is greater than alpha, h0 is not rejected. As discussed, the probability of getting a sample statistic as extreme as this one from the hypothesized value is not rare. In other words, it is normal to have a sample statistic as high as this one due to just chance variance. And therefore, the evidence from the sample is not sufficiently strong enough to reject H0. If the area to the right of x bar or p is less than or equal to alpha, then H0 is rejected. As per the illustration, H0 will not be rejected since the area to the right of x bar or p is greater than alpha in this case. In general, for any value of x bar or p greater than the critical value x bar star or p star, H0 will be rejected. On the other hand, for any value of x bar or p less than or equal to the critical value x bar star or p star, H0 will not be rejected. H0 will not be rejected even for values of x bar or p smaller than the hypothesized value. That's because, as we have already learned, that the null hypothesis mu or pi equals hypothesized value also implies mu or pi is less than or equal to the hypothesized value in this case. Let's take the next case, case 2, where the alternative hypothesis HA is mu or pi is less than the hypothesized value. Sample is drawn from the population and the sample statistic x bar or p is computed. Area under the statistic distribution to the left of x bar or p, the shaded part, is evaluated. This shaded area provides the probability of getting a sample statistic as extreme as the current one, meaning the current one and values lesser than the current one from the hypothesized value. This area is compared with the value of alpha, that is the shaded area shown above. If the area to the left of x bar or p is greater than alpha, H0 is not rejected. If the area to the left of x bar or p is less than or equal to alpha, then H0 is rejected. As per this illustration, H0 will not be rejected since the area to the left of x bar or p is greater than alpha. In general, for any value of x bar or p less than or equal to the critical value x bar star or p star, H0 will be rejected. On the other hand, for any value of x bar or p greater than the critical value x bar star or p star, H0 will not be rejected. H0 will not be rejected even for values of x bar or p larger than the hypothesized value. That's because, as we have understood, the null hypothesis mu or pi equal to hypothesized value implies mu or pi is greater than or equal to hypothesized value in this case. Let's take the last case, case 3, where the alternative hypothesis HA is mu or pi not equals hypothesized value. Sample is drawn from the population and the sample statistic x bar or p is computed. Calculate the value pair SL and SH, where SL equals hypothesized value minus the absolute value of the difference between x bar or p minus the hypothesized value, and SH equals hypothesized value plus the absolute value of the difference between x bar or p minus the hypothesized value. Note, SL and SH are symmetrical with respect to the hypothesized value. Since the shaded areas under the statistic distribution to the left and right of SL and SH are equal due to symmetry, the total shaded area equals 2 times the shaded area to the left of SL. The total shaded area provides the probability of getting a sample statistic as extreme as the current one or as deviating as the current one from the hypothesized value. If the total shaded area is greater than alpha, H0 is not rejected. If the total shaded area is less than or equal to alpha, H0 is rejected. As per the illustration, H0 will not be rejected since the total shaded area appears visibly greater than alpha. In general, for any value of x bar or p in the range x bar or p greater than CV left and less than CV right, H0 will not be rejected. For any other value of x bar or p, wherein x bar or p is greater than or equal to CV right and less than or equal to CV left, H0 will be rejected. The shaded areas to the right and left of x bar or p discussed so far are the probabilities of getting a sample statistic as extreme as the current one, assuming that H0 is true. This shaded area is called as the p-value. While alpha is called as the level of significance of the hypothesis test, p-value is referred at times as observed significance level. P-value is a measure of inconsistency between the hypothesized value for the population characteristic and the observed value. Having understood how the decision is made between H0 and HA, based on the p-value of getting a sample statistic as extreme as the one from the current sample, for each of the following three cases, the next step is to understand how to compute this probability, that is the p-value. Computing the p-value for x bar or p directly on the sample statistic distribution is tedious. Hence, computing this probability is carried out on the respective standard normal distributions. Refer previous lectures on sampling mean distribution and central limiting theorem and sampling distribution of sampling proportion. Let's dive into the math to arrive at the p-value associated with a sample statistic. So far in our discussions, we kept the sample statistic x bar or p together, since the concepts that we discussed so far apply to both x bar and p. It is now the time that we have to deal with them independently because the mean and the standard deviation play an important role in evaluating the probabilities, that is the p-value, and mean and standard deviation characteristics are computed differently for the sample proportion statistic p distribution and the sample mean statistic x bar distribution. Let's start with the sample proportion statistic p distribution. Please recall, sampling distribution of sample proportion p is close to normal when n pi is greater than or equal to 10 and n multiplied by 1 minus pi is greater than or equal to 10, where n is the sample size and pi is the population proportion of success. Where the mean of the sample proportion p distribution mu p equals pi, that is the population proportion of success, and which in turn also equals hypothesized value because we arrive at p-value on the statistic distribution where the mean happens to be equal to the hypothesized value. And the standard deviation of the above distribution, sigma p, equals square root of pi multiplied by 1 minus pi divided by n. Sample proportion p arrived out of a sample corresponds to a value z star on the standard normal distribution, where z star equals p minus hypothesized value divided by sigma p. Z star is often referred as the test statistic. The test statistic is a function of the sample data that decides either H0 should be rejected or not, that is, fail to reject H0. Assuming the hypothesis under test are H0, that is pi equals hypothesized value, and HA, that is pi is greater than hypothesized value, we are interested in computing the area, that is the p-value, under the z-curve to the right of calculated z star. P-value equals 1 minus probability of z taking a value less than z star. We pick the probability of z taking a value less than z star from the z table using the value of z. Refer previous lectures on z table for this and evaluate the above expression for p-value. If p-value is greater than alpha, then H0 is not rejected. Else if p-value is less than or equal to alpha, then H0 is rejected. Suppose the hypothesis under test are h0, that is pi equals hypothesized value, and ha, that is pi is less than hypothesized value, and the p and the z star values are shown besides. P value in this case is the area under the z curve to the left of the calculated z star. P value equals probability of z taking a value less than z star. We pick probability of z taking a value less than z star from the z table using the value of z and evaluate the expression for p value. If p value is greater than alpha, then h0 is not rejected. Else if p value is less than or equal to alpha, then h0 is rejected. The last set of hypotheses that we need to test are h0, that is pi equals hypothesized value, and ha, that is pi not equals hypothesized value, and the p and the corresponding z values are as shown besides. Since p is greater than hypothesized value in this case, p value is 2 times the area under the z curve to the right of the calculated z star. P value equals 2 times of 1 minus probability of z taking a value less than z star. We pick probability of z taking the value less than z star from the z table using the value of z and evaluate the above expression for p value. If p value is greater than alpha, then h0 is not rejected. Else if p value is less than or equal to alpha, then h0 is rejected. Note that alpha is divided symmetrically into 2 parts at either ends of the distribution. For the same hypothesis, let's now consider value of p less than hypothesized value and the corresponding z star value as shown besides. Since p is less than hypothesized value, p value in this case is 2 times the area under the z curve to the left of the calculated z star. P value equals 2 times the probability of z taking a value less than z star. We pick probability of z taking a value less than z star from the z table using the value of z. If p value is greater than alpha, then h0 is not rejected. Else if p value is less than or equal to alpha, then h0 is rejected. That concludes the illustration of calculating the p value for various scenarios when the sample statistic is a sample proportion of success. Now let's turn our attention towards the case where the sample statistic is a sample mean and understand calculating the p-value for various scenarios. Please recall, sampling mean distribution is close to normal when the sample size n is greater than or equal to 30 or when the population distribution itself is normally distributed. With mean of the sample mean distribution mu x bar equals mu, that is the population mean, and which also equals the hypothesized value for the same reasons that we discussed in the case of sample proportion distribution, and the standard deviation of the above distribution sigma x bar equals sigma divided by square root of n, where sigma is the standard deviation of the population. We start with the case where sigma is known. In fact, the above formula for sigma x bar applies only in the case where the population standard deviation sigma is known. When the population standard deviation sigma is known, sample mean x bar arrived out of a sample corresponds to a value z star on the standard normal distribution, where z star equals x bar minus hypothesized value divided by sigma x bar. When the population standard deviation sigma is not known, sample mean x bar arrived out of a sample corresponds to a value t star on the standard t distribution corresponding to a given degree of freedom df, where t star equals x bar minus hypothesized value divided by s divided by square root of n, where S is the sample standard deviation, n is the sample size, and the degree of freedom df equals n minus 1. Note, calculation of the test statistic z star or t star is the primary difference between the scenarios discussed involving sample proportion just a while ago and the sample mean being discussed now. Rest of the decision making step remain the same for each of these scenarios. For the hypothesis H0, that is mu equals hypothesized value, and HA mu is greater than the hypothesized value. Like in case of sample proportion distribution, p-value happens to be the area under the z-curve or the t-distribution to the right of the calculated test statistic z star or t star respectively. P-value therefore equals 2 times 1 minus probability of z or t taking a value less than z star or t star respectively. P-value is evaluated using the value of z star or t star from the z table or the t table respectively, as discussed in the previous cases. If p-value is greater than alpha, then H0 is not rejected. Else if p-value is less than or equal to alpha, then H0 is rejected. For the second set of hypotheses, H0 mu equals hypothesized value and HA mu is less than hypothesized value, and a sample mean value x bar as shown beside. P-value is the area under the z-curve or the t distribution to the left of the calculated test statistic z star or t star. P-value equals 2 times the probability of z or t taking a value less than z star or t star respectively. If p-value is greater than alpha, then H0 is not rejected. Else if p-value is less than alpha, then H0 is rejected. The last set of hypotheses, H0, that is mu equals hypothesized value, and HA mu not equals hypothesized value, and a sample mean value x bar greater than the hypothesized value. P-value is twice the area under the z-curve or the t distribution to the right of the calculated test statistic z star or t star. P-value equals 2 times 1 minus probability of z or t taking a value less than z star or t star respectively. If p-value is greater than alpha, then H0 is not rejected. Else if p-value is less than or equal to alpha, then H0 is rejected. And for a sample mean value x bar less than hypothesized value, p-value is twice the area under the z-curve or the t distribution to the left of the calculated test statistic z star or t star. P-value equals 2 times probability of z or t taking a value less than z star or t star respectively. If p-value is greater than alpha, then H0 is not rejected. Else if p-value is less than or equal to alpha, then H0 is rejected. That brings us to the end of the lecture on applying the concepts. We understood how to apply the characteristics of the probability distribution to decide from a sample statistic to whether reject the null hypothesis or not. Then how to apply the level of significance alpha and how to calculate the p-value from the sample statistic, and finally make the decision between H0 and HA for two different population characteristics, namely population proportion of success and population mean. In the next lecture, we will take specific examples and apply the concepts we learned in this lecture to arrive at the decision between H0 and HA. See you soon back with the next lecture. Bye.